Hello class, and welcome to this lesson for section 8.4 and 8.5. This will cover rate of change, which is section 8.4, and direct variation, which is section 8.5. By the end of the lesson, you will be able to identify rates of change and also identify and apply direct variation. So starting with rates of change, a rate of change is how the y values change in relation to the x values. This change can be positive, negative, or zero. When it is a constant rate of change, this is the rate between 2 points in a linear relationship. So if we look at the three examples down here at the bottom, this first one shows a positive rate of change, and it is constant. It is a line that is going up by the same amount as it continues to go from left to right. This second example is also a constant rate of change. Once again, it is a line going down from left to right. So this would be a negative rate of change. This third example here is a positive rate of change. It is going up, but it is not constant. So what that means is that we start going up by a little bit, and then by the end of this, we're going up super fast. So the rate changes over the course of the graph. So we're going to do some investigating. This graph right here, we have a lot of different rates of change. So between each point, the changes are different. So between point A and point B, you'll notice it's a flat line. That's when we have a rate of change of 0. So we start at 2,000 and we end at 2,000 over the course of that movement. So this A to B is an example of a 0 rate of change. Then for part A, it wants us to find the rate of change between point E down here and point F up here. So our definition for rate of change said the change of the y values compared to the change of the x values. So I look at my y values first, and I'm going to say for the y's, I have going from starting at 2000, going up to 2008. So it's from 2000 to 2008. So that gives me 800. We went from 2000 up to 2008, which was a positive 800. Then I'm looking at my x's. I started with point E at 1,400, so from 1,400 to going over to F is right in between here, so that's 1,600. So that is a change of 200. Then when I write my answer, my rate of change, I'm going to abbreviate that to ROC, changes 800 feet vertically for every 200 feet horizontally. When you do this, now you look at your fraction and say, can I reduce that? In this case, we can. We can divide both values by 200. So your final answer for the rate of change between point E and point F is going to be 4 feet vertically for every 1 foot horizontally. And you want to make sure you put these labels on your rates so you know what you are talking about. I want you to go ahead now and try to find the rate of change for point C to D on your own. And we're going to start by finding the y's. So what is the change in the y's? Now that we have the y's, which go from negative 2,400 down to 2,000, I want you to find the x's. The x's go from 800 to 1,100, so a change of 300. Now I want you to find the reduced form of the rate of change with the labels. When I find that reduced form, I end up with negative 400 feet vertically over 300 horizontally reduces to negative 4 feet vertically for every 3 feet horizontally. We also then have constant rates of change. That's when we get into these linear relationships. So the last graph, the rate of change changed over time. A to B was different from B to C, which was different from C to D, which was different from E to F, which was different from D to E. So each segment had its own rate of change. When we get into linear relationships, like this graph shows, we have a constant rate of change. So it's going up or down by the same amount. So I'm going to start by looking at the one labeled circle 1. I want to start by looking at my y's. So for the y values, I'm looking for points on the graph. We can't really tell what this dot is right here, but I can tell that this one is 5 and this one right here is 4. So for the y's, I went from 5 to 4, so -1. Then I want to look at my x's. And when I take those 2 points, I started at 2 and I went over to 6. So from 2 to 6, so that gives me 4. Then my rate of change value becomes -1 centimeters over 4 seconds, meaning that for every we lose 1 centimeter of the radius every 4 seconds. And that comes from reading the labels on the graph. So -1 means we're losing 1 centimeter of the radius, because that's our label, for every 4 seconds. I want you to go ahead and now do circle 2. So starting with the y's, what do we have for the y's? For the y's, we're going from 3 to 6, so a change of 3. Now I want you to do the x's. So from 2 to 4 gives you a change of 2. Now I want you to state the rate of change with its meaning. So we have our rate of change of 3 over 2, which means 3 centimeters bigger for every 2 seconds. So again, these constant rate of changes happen when we are looking at lines. We can also pull these things out from a table. So we have for this one, a CD is spinning at different rates based on whether the songs are on the inside of the CD versus the outside of the CD. If you think about a CD, some of you probably have seen these before, the inside is a much tighter circle and the outside is a bigger circle. So if we're looking at the inside, we're going to start with those y's. So for my y's, I've got starting with, I can either pick from 0 to 16 or from 16 to 32, because those are both the same amount. So I'm just going to go from 16 to 32, which is 16. Then I've got my x's. So my x's go from 2 to 4, so 2. That gives me my rate of change being 16 over 2. And when I interpret that meaning, that's going to give me 8 revolutions every 1 second. Now I want you to go ahead and find the y's for the outside. So we go from 0 to 6 or from 6 to 12, and that's a change of 6. Now find the x's. So we go from 0 to 2 or from 2 to 4. That is going to be a change of 2. Now I want you to find that rate of change. That's going to be 6 over 2, which is 3 revolutions every second. So for our comparison then, you can say one of two things. You can say the inside spins 5 revolutions faster per second. Or you could state it the other way and say the outside spins 5 revolutions slower per second. So you would need to state one of those two things as your comparison. You don't need to have both. You either need to have the first one or the second one. So that lets us look at two different rates and compare how they are moving. If you need a summary of this, you can find this in your textbook on page 414. Gives you an idea of what the graph would look like, what the meaning is, and what we actually call it. So positive going up, example on the graph, negative going down, example on the graph, and then that zero change, that flat line that we talked about from the first graph. Now, when we're looking at these lines, that's what we're going to start getting into for the rest of Chapter 8, is how we can use these rates of change to describe lines. The first type of line we're going to talk about is called a proportional line or a direct variation line. This happens when the ratio of x and y is constant. So, our x value then cannot be 0, because what we're talking about when we have a ratio is this fraction. Our x value can't equal 0 because we can't divide by 0. As I said, these are also called direct variation relationships, and you can tell that they are proportional relationships by looking either at the ratios, determining if y over x is the same, or by looking at the graph and seeing, does it go through the origin? Does it go through 0, 0? If a graph goes through 0, 0, it is proportional. If it doesn't go through 0, 0, it's not proportional, which we can double check this. So the ratio here would be 4 over 1 for the first point, 8 over 2 for the second point, and 12 over 3 for the third point. 4 over 1 is 4, 8 over 2 is 4, 12 over 3 is 4. On this second graph, I again have 4 over 1, but the next point is 6 over 2, and the last point is 8 over 3. 4 is not the same as 3, which is not the same as 2 and 2/3. So if it doesn't go through 0, we're not going to have this proportional equation. To write a direct variation, it's written in the form y equals kx. And again, that k is the ratio, the y divided by the x. So, looking at identifying, this first one, they give us a graph. As I just said, if it goes through 0, 0, this would be a proportional or a direct variation relationship. I want you to go ahead and decide, is this table, which is a separate problem, it does not relate to problem A, is this table showing a proportional relationship? The answer here is not proportional because 4 over 1 is not equal to 6 over 2, and 6 over 2 is not equal to 3 over 12. So even though the first pair and the third pair are proportional, that second pair doesn't match up, so the whole thing is non-proportional or not direct variation. When we do have direct variation, we can write the equation and use them to solve these problems. So we can use this constant rate to solve the problem. So it says the time it takes to download an app directly varies with the amount of information, aka the size of the app. It tells you it's direct variation. You can also double check that by dividing any of these values. 10 divided by 2.5, 15 divided by 3.75, 40 divided by 10, 100 divided by 25. When you do all of that dividing, I'm just going to pick one with whole numbers because I like those the best. So I'm going to say 40 divided by 10. All of those are going to divide to give you k is equal to 4. Then it asks you to write the direct variation equation. That's saying y equals kx, but in this case, we know that our k we just solved is equal to 4. That is the equation. That is the first direction they give you. Then it asks you to predict how long it will take to download an app that is 700 megabits. So 700 megabits then is an x value. So for the second part of the problem, you're going to say 4 times 700, and that's going to give you y is equal to 2,800, and the label on that is seconds. If you wanted to convert it into something a little bit more practical, you could divide it by 60, and that's going to give you 46 minutes and 40 seconds. So if you wanted to convert it, you can, or you can just leave your answer as 2,800 seconds. Next example, they give us a graph and they tell us the cost of apples directly varies with the pounds that you are buying. Use the graph to write the direct variation equation. So first, I want you to determine the value of K. So we have a K value of 0.8. Now I want you to write the direct variation equation. That's going to give you y is equal to 0.8x. Then it asks you to determine the cost of 5 pounds. So I want you to determine the cost of 5 pounds. That's going to be 0.8 times 5, and that is going to be $4 for 5 pounds of apples. If you have questions about this or anything else from the lesson, please feel free to reach out and let me know.